Welcome to Study Loop.
Hi there. So for this problem, we are given the information that a patient is placed within a strong magnetic field. Now, um, we are told about the area through which this magnetic field is passing through, and that area has a value of 0.032 meters squared, and it is in a normal, so that is parallel to the magnetic field, and that magnetic field has a value of 1.5 Tesla. And so we need to determine the smallest time period such that the field can be allowed to vanish, and the magnitude of the induced nth is also given, and that value is 100 0.010 volts. So that's the information for this problem. Now we know that an nth that is induced in the body, and in this case, because of the magnetic flux, is changing, of course, in time according to Faraday's law. We know that is the magnitude of the nth is equal to the magnitude of minus the number of turns times the change in the flux and magnetic flux over the interval of time. Now, from this, we can use this expression to determine the interval of time during which these magnetic fields goes from its initial value, that is this value in here, to a final value that is going to be 0. So that final value of the magnetic field, we're going to call this the initial one, and this one, that is the last one, is going to be 0 Tesla. Now, the magnetic flux is obtained from this equation that we know, that is the flux is equal, let me put this in here. The flux is equal to the product between the magnetic field times the area times the cosine of the angle that the normal of the surface mates with the magnetic field vector. Now in this case, that angle is 0, so we will obtain cosine of 0, which is 1. So we obtain just this product in here. Now we can put this into this equation, but we know that is the change in the magnetic field, and that will be the initial magnetic field, the final magnetic field times the area minus the initial magnetic field times the area. In this case, the area is the same. We are not changing the area. We're changing the magnetic field. So that will be B minus B0. Now we can substitute right now that in there and solve for the delta time. So solving for delta t, we obtain that delta t is equal to is going to be minus n times delta, the change in the flux, over the magnitude of the nth. So we introduce all that we have obtained. So that is this, the change in the magnetic flux is this one in here. So that is A times B minus B0, and all of this over the nth. We know all of these values, so we just substitute that in there. We know that the number of thorns, that capital N, is just 1. We have 1 thorn, so that will be minus 1 times the area, which is 0.032 meters squared, times the difference between the final magnetic field and the initial one. So the final is just when it is 0, and the initial one is 1.5 Tesla. So in here we can see that these two signs canceled, and we will have this over the fem. That fem, and we are also given the value for that, that is 0.010 volts. So introducing this into the calculator, we obtain that the interval of time so that the field is allowed to vanish is equal to 4.8 seconds. So this is the solution for this problem.